Late March, 1945. Kummersdorf Proving Ground. Brandenburg, Germany. The captured M18 Hellcat sat in Bay 7 of the testing facility, its American White Star hastily overpainted with Balkan crosses that fooled no one. Hauptmann Friedrich Weber circled the vehicle slowly, notebook in hand, studying the impossibly thin armor with something approaching disbelief. This tank destroyer, serial number USA 4092837, had been captured nearly intact near Cologne 3 weeks earlier. Its crew had abandoned the vehicle after track damage from artillery fragments left it immobile during a chaotic withdrawal. German recovery teams, accustomed to finding burned-out American hulks, were stunned when this one started on the first try despite sitting under fire for 6 hours. The numbers painted on its hull told Weber everything he needed to know about why this vehicle terrified him. 18.4 tons, 55 miles per hour maximum road speed. That second figure made his stomach tighten. 55. His own Panzer IV, a vehicle the Wehrmacht considered adequately mobile, managed 25 miles per hour on good roads with a favorable wind. The Panther, Germany's supposed answer to American tank destroyers, hit 30 miles per hour in ideal conditions and broke down trying. This American machine, this collection of welded steel plates that looked like it belonged on a racetrack instead of a battlefield, could outrun his staff car. Weber had commanded a panzer company through 2 years of fighting on the Eastern Front. He understood armor mathematics, the brutal calculus of gun penetration versus plate thickness, the geometry of angled impacts and kill zones. He knew that his Panther's 75mm gun could kill any Soviet tank at ranges where return fire was impossible. But this Hellcat changed the equation in ways that made his carefully learned doctrine feel obsolete. Because a tank you couldn't catch was a tank you couldn't kill. And a tank that could appear anywhere, at any time, moving faster than your turret could traverse, rendered all that careful mathematics irrelevant. The High Command had issued explicit orders. This vehicle must be tested exhaustively, photographed from every angle, driven until something broke, measured against German equipment in direct comparison trials. The results would be classified, naturally, but Weber already suspected what those results would show, because he'd driven German armor long enough to understand what speed meant on a battlefield where the entire eastern border was collapsing inward. The Americans had built something that didn't just challenge German technical superiority. It mocked the entire philosophy behind German tank design, and Weber, standing in that cold testing bay with early spring sunlight filtering through the overhead skylights, realized he was about to document the evidence of exactly how badly Germany had miscalculated what mattered in armored warfare. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The testing protocols had been prepared weeks earlier, anticipating that eventually an M18 would fall into German hands intact enough to examine. Kummersdorf maintained standardized procedures for evaluating captured equipment, refined through 3 years of studying knocked-out Soviet tanks, recovered British vehicles, and the occasional American Sherman. But the Hellcat presented unique challenges because its capabilities seemed to violate fundamental assumptions about combat vehicle design. Oberingenieur Hans Richter led the technical assessment team. A veteran engineer who'd worked on German armor development since before the war, Richter had overseen testing on dozens of captured vehicles. He approached each examination with methodical precision, measuring dimensions with calipers, documenting construction techniques with detailed photographs, analyzing design choices that revealed enemy industrial capabilities and tactical priorities. The initial inspection of the M18 took 2 full days. Richter's team measured armor thickness at 47 different points across the hull and turret, recording each figure with annotations about welding quality, plate angles, and structural reinforcement patterns. The frontal glacis plate measured 1 inch thick, the turret front 1 inch, side armor 3/4 of an inch, rear hull plates 1/2 inch in some locations. These figures horrified German tankers who reviewed the reports. A Panzer IV had 50mm, nearly 2 inches, of frontal armor. A Panther had 80mm, over 3 inches, sloped at 55 degrees for effective thickness exceeding 5 inches against perpendicular impacts. Tiger tanks boasted frontal armor over 4 inches thick in places. The Americans had built a tank destroyer with armor that wouldn't stop a standard anti-tank rifle from close range. Yet combat reports from the Western Front described M18s hunting Panthers and Tigers, achieving kills, and escaping before German crews could respond. The contradiction demanded explanation. Richter found part of that explanation in the vehicle's construction, where German tanks used complex welding techniques requiring skilled metalworkers and precise fitting. The Hellcat employed simplified welded construction that sacrificed elegance for manufacturing speed. Plates were cut at straight angles rather than complex curves. Welds were heavy and obvious rather than carefully ground smooth. The entire hull showed evidence of mass production techniques prioritizing output over appearance, exactly the approach Soviet factories had mastered and German industry had resisted adopting. The engine bay revealed more uncomfortable truths. The Wright R975 radial engine, an air-cooled design originally developed for aircraft use, sat in a compartment that looked impossibly simple compared to German powertrain installations. Richter had spent months analyzing captured Sherman tanks that used the same engine family. He understood its reliability profile, its tolerance for varied fuel quality, its resistance to overheating in desert conditions that destroyed German cooling systems. But seeing that same engine in a vehicle weighing nearly 40% less than a Sherman made the performance implications obvious. The M18's power-to-weight ratio exceeded anything in German service, 26 horsepower per ton compared to 15 for a Panzer IV, 13 for a Panther. That gap explained why American crews could accelerate out of ambush positions before German gunners completed target acquisition. It explained why M18s appeared and vanished like ghosts in the confused fighting across France and into Germany. The transmission examination provided additional shock. American engineers had adapted the Cadillac Hydromatic automatic transmission, a civilian design proven in hundreds of thousands of automobiles, for military use in the M18. Richter had examined hydromatic transmissions before in other captured American vehicles. He understood intellectually what they represented, but seeing one in a combat vehicle that outperformed his own equipment made the achievement feel personally insulting. German tanks used manual transmissions with straight-cut gears requiring double clutching and careful throttle management. Drivers needed extensive training to shift smoothly without grinding gears or damaging the transmission under combat stress. The Panther's transmission, notoriously fragile, could fail catastrophically if shifted incorrectly, leaving 60-ton vehicles immobile and requiring complete drivetrain replacement. The Hellcat's automatic transmission meant any soldier who could drive a civilian car could operate this vehicle competently within hours. No special training for clutch, timing. No risk of operator error, destroying expensive components. The system simply worked, shifting smoothly under acceleration and allowing drivers to focus on navigation and tactical positioning rather than mechanical operation. Richter documented this with detailed photographs and precise technical drawings. He wrote in his preliminary report that the Americans had achieved through automotive mass production what German industry had failed to accomplish through precision engineering, creating reliable mechanical systems that ordinary soldiers could operate and maintain under field conditions without specialized expertise. The suspension system reinforced this pattern. The M18 used torsion bar suspension, the same basic technology found in German tanks, but where German designs emphasized theoretical optimization, accepting complexity for marginal performance gains, the American implementation prioritized simplicity and maintainability. Each torsion bar could be removed and replaced without disassembling adjacent components. Road wheels were interchangeable. Shock absorbers used standard automotive parts available in any reasonable supply depot. German tankers knew intimately the nightmare of field repairs on their own equipment. Replacing a broken torsion bar on a Panther required partially disassembling the sponson, carefully extracting the damaged unit without disturbing neighboring systems, then precisely installing and adjusting the replacement. The job took trained mechanics with proper tools most of a day to complete. On an M18, The same repair required basic hand tools and 4 hours of work by moderately skilled personnel. Richter's team photographed every accessible component. They measured clearances, documented assembly sequences, and prepared detailed technical drawings showing how American engineers had designed for maintenance from the beginning. Each design choice reflected practical field experience and automotive industry knowledge applied to military requirements. German designs reflected theoretical engineering excellence applied without sufficient consideration for the reality of combat maintenance under field conditions. The gun system examination revealed further American advantages. The 76mm M1A1 gun, while not dramatically more powerful than German 75mm weapons, incorporated features that improved practical battlefield effectiveness. The elevation and traverse mechanisms used electric motors for fine adjustment, allowing gunners to track moving targets smoothly. Backup manual controls ensured operation even if electrical systems failed. The gun sight, a straightforward telescopic design without exotic optics, nonetheless provided adequate magnification and clear target identification at combat ranges. More importantly, it could be removed and replaced as a complete sealed unit without requiring precision optical alignment in the field. German gun sights, technically superior in many respects, required expert adjustment after installation and could be rendered useless by impacts that left American sights functional. Ammunition stowage showed characteristic American pragmatism. 45 rounds of 76mm ammunition fit in racks designed for rapid access and positive retention. Rounds couldn't shift loose during violent maneuvers. Loaders could grab ammunition by feel in darkness or under stress. The arrangement accepted slightly reduced total capacity in exchange for faster sustained firing rates and reduced risk of ammunition cooking off if the vehicle was penetrated. German ammunition stowage varied by vehicle type, but generally prioritized maximum capacity over ergonomic access. Panthers carried 82 rounds of main gun ammunition, but loaders often struggled to extract rounds from poorly positioned racks during combat stress. The Americans had accepted carrying fewer rounds in exchange for every round being immediately accessible, a trade-off that made tactical sense given their doctrine of rapid engagement followed by withdrawal. After 2 days of static examination, Richter authorized powered testing. German mechanics had already verified that all systems functioned. The engine started reliably, running smoothly at idle. The transmission shifted through all ranges without hesitation. Controls responded normally. But Richter needed quantitative data on performance characteristics to complete his evaluation. Hauptmann Weber would conduct the driving trials himself. As a combat veteran with extensive experience operating German armor, Weber could provide credible comparison between American and German vehicles based on direct personal experience rather than theoretical analysis. Richter's team prepared instrumentation to measure acceleration, braking distances, turning radius, fuel consumption, and maximum speed across various terrain types. The morning of March 28, 1945, dawned clear and cold. Weber climbed into the M18's driver position, noting immediately how different the layout felt compared to German tanks. The seat was adjustable, a simple feature German designers apparently considered unnecessary. Controls fell naturally to hand without stretching. Forward visibility exceeded anything Weber had experienced in German armor, the vehicle's low profile and well-positioned viewports, giving the driver genuine situational awareness. He started the engine, feeling the radial's distinctive vibration through the hull. Richter stood beside the vehicle with a stopwatch and clipboard, ready to record performance data. Other engineers positioned themselves at various points around the testing track, with timing equipment and theodolites for measuring turning performance. Weber released the brake and fed throttle. The Hellcat lunged forward with acceleration that shocked him despite knowing intellectually what the power-to-weight ratio suggested. The automatic transmission shifted smoothly through gears as speed built. Within seconds, the vehicle was moving faster than any German tank could achieve. The ride quality, surprisingly smooth for a tracked vehicle, allowed Weber to maintain high speed without being battered by suspension harshness. He drove the marked course, a 2-kilometer circuit combining straight sections, curves of varying radii, and grade changes simulating battlefield terrain. The Hellcat handled it effortlessly. Acceleration from standing start reached 25 miles per hour in 8 seconds. Maximum observed speed on the straight section exceeded 50 miles per hour, limited by Weber's nervousness rather than vehicle capability. Braking performance from high speed was dramatic, the Hellcat shedding velocity rapidly without losing directional control. Turning at speed produced noticeable body lean but remained controllable, the torsion bar suspension managing weight transfer adequately. Weber completed 3 circuits, each run building his confidence in the vehicle's capabilities and simultaneously deepening his dismay at what those capabilities meant for German armor tactics. When he finally shut down the engine and climbed out, Weber's expression told Richter everything before any words were spoken. The American vehicle had just demonstrated performance that made German tactical assumptions obsolete. A tank destroyer that could reach threatened sectors faster than any panzer division could redeploy, that could engage from ambush and vanish before supporting units could respond, that could choose when and where to fight with complete tactical freedom. Richter recorded Weber's observations in detailed notes. Vehicle extremely responsive to driver inputs. Acceleration exceeds all German armor by substantial margin. High-speed handling confident and stable. Visibility excellent, superior to German equipment. Controls intuitive, requiring minimal specialized training. Operational range adequate for sustained operations without frequent refueling. Noise signature less than expected given performance capability. Each notation added to a report that would eventually reach headquarters in Berlin, though whether anyone there would read it before Soviet forces overran the city was increasingly questionable. But Richter maintained professional standards regardless of broader strategic reality. His job was documenting technical truth, not managing Germany's collapse. The comparative testing began the following day. A Panzer IV Ausf H, Germany's most numerous medium tank, was brought from storage to run the same course Weber had driven in the Hellcat. The Panzer IV represented mature German tank design, with adequate armor, reliable automotive systems by German standards, and proven combat effectiveness. It was the baseline against which newer German and all captured enemy vehicles were measured. Lieutenant Klaus Schneider, a test driver with hundreds of hours operating German armor, conducted the Panzer IV trials. He drove the marked course carefully, pushing the vehicle to its limits without risking mechanical failure. The results, measured precisely and documented thoroughly, confirmed what everyone already knew, but seeing the numbers written in official reports made the disparity undeniable. Acceleration from standing start to 25 miles per hour required 18 seconds in the Panzer IV, more than twice as long as the Hellcat. Maximum speed reached 28 miles per hour on the straight section, barely half the American vehicle's capability. Turning radius at speed was significantly larger, the Panzer IV's longer hull and less sophisticated suspension limiting maneuverability. Braking distances exceeded the Hellcat's by nearly 40%. Fuel consumption figures added insult to technical defeat. The Hellcat, despite dramatically superior performance, used less fuel per kilometer than the Panzer IV. American automotive engineering efficiency, proven through decades of civilian vehicle development, translated directly into improved military vehicle economy. German tanks, designed by talented engineers who nonetheless lacked America's depth of practical manufacturing experience, consumed fuel at rates that strained logistics systems already near collapse. Richter prepared comparison charts showing performance metrics side by side. Every category except armor thickness and gun penetration favored the American vehicle, and even those traditional measures of tank capability mattered less than German doctrine assumed, because a Panzer IV that couldn't catch an M18 couldn't bring its superior armor and firepower to bear. The testing continued through early April as Richter's team exhausted every evaluation protocol. They measured track durability by running the Hellcat over obstacle courses designed to stress suspension and running gear. They tested engine performance under varied loads and terrain conditions. They evaluated maintenance accessibility by having mechanics perform standard service procedures, timing each task, and documenting required tools and parts. Every test produced results that reinforced uncomfortable conclusions. American automotive engineers had applied mature industrial knowledge to military vehicle design and produced equipment that worked better in practical field conditions than German vehicles designed by theoretically superior engineers. Working within an industrial system that couldn't match American manufacturing sophistication, the M18's track system exemplified this pattern. German tracks used pin connectors, requiring careful installation and frequent adjustment to maintain proper tension. American tracks used rubber-bushed pin assemblies that self-centered during installation and maintained tension automatically across wider adjustment ranges. The difference meant German crews spent hours weekly adjusting track tension, while American crews checked tension monthly and rarely needed adjustment. Road wheels showed similar practical advantages. German steel wheels with rubber tires required specialized tire mounting equipment and skilled labor. American cast wheels with integral rubber pads could be replaced completely as assemblies without special tools. Individual wheel removal for bearing service took German mechanics 4 hours with proper equipment. American mechanics completed the same repair in 90 minutes with basic hand tools. These weren't dramatic technological breakthroughs. They were accumulated refinements from decades of American automotive manufacturing experience, each small improvement, insignificant, individually, but collectively representing the gap between an industry that had mass-produced millions of vehicles and one that built smaller numbers of individually more sophisticated machines. Richter documented everything meticulously. His reports would eventually fill 3 folders containing hundreds of pages of technical analysis, performance data, and detailed photographs. The conclusions were inescapable and damning. Germany had lost the automotive war before the shooting started, because German industry had never developed the depth of practical manufacturing experience that American factories possessed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By mid-April 1945, testing at Kummersdorf had become increasingly surreal. Soviet artillery could be heard in the distance on quiet days, a rumble that grew perceptibly closer week by week. Staff at the Proving Ground understood intellectually that the war was ending, that their meticulous technical work would soon become footnotes in history written by victors. But German professionalism demanded completing assigned tasks regardless of strategic futility. Weber had driven the M18 dozens of times by then. Each drive reinforced his assessment that American tank destroyer doctrine, which had seemed reckless when first described in captured field manuals, actually made brutal tactical sense when paired with equipment this capable. The Hellcat wasn't trying to be a tank. It was something different, a specialized killing machine that redefined the parameters of armored engagement. Traditional tank warfare assumed relatively matched opponents maneuvering for positional advantage, trading fire at ranges where armor and gun penetration determined outcomes. The M18 rejected those assumptions completely. It didn't trade fire. It fired first from ambush, then vanished before return fire became possible. Its thin armor wasn't a compromise accepted reluctantly. It was a deliberate design choice that enabled the speed making that tactical approach viable. Weber had commanded Panthers in combat. He understood intimately how Panther crews fought, the careful positioning to maximize frontal armor advantage, the methodical target acquisition through superior optics, the confidence that 80mm armor plates provided against most enemy weapons. All those carefully learned tactical principles became irrelevant against an opponent that never gave you the engagement you'd trained for. A Panther versus M18 engagement wouldn't be won by the superior gun or thicker armor because the M18 wouldn't fight that battle. It would appear suddenly at close range, fire into the Panther's thinner side armor before the German crew completed their traverse, then accelerate away at 50 miles per hour while the Panther lumbered after it at 30. The mathematics were simple and brutal. Speed beat armor when you controlled engagement terms. Richter had reached similar conclusions through different analysis. His technical reports emphasized industrial capacity and manufacturing philosophy rather than tactical employment. but the fundamental conclusion aligned with Weber's combat veteran assessment. Germany had built tanks optimized for set-piece battles against peer opponents. America had built tank destroyers optimized for fluid defensive operations against armored breakthroughs. German doctrine assumed battles would be won through technical superiority and tactical skill. American doctrine assumed battles would be won through industrial overwhelming force, applied flexibly across changing circumstances. The M18 embodied American philosophy perfectly. Good enough, technically, vastly superior numerically, and employed with tactical flexibility that made theoretical performance advantages irrelevant. The last formal test occurred on April 19, 1945. A Panther OSV-G, representing Germany's most effective mass-produced tank, was brought to Kummersdorf for direct comparison trials. The Panther was everything German engineering could be when functioning properly. Powerful gun, excellent armor, sophisticated fire control, and reasonable mobility when the notoriously fragile transmission cooperated. Weber drove the Panther through the same course he'd run in the M18 weeks earlier. The vehicle felt massive and ponderous after the nimble American machine. Acceleration was adequate but unimpressive. Maximum speed reached 32 miles per hour on the straight section, respectable for a vehicle weighing 45 tons but still 30% slower than the Hellcat. The Panther's superior gun and armor provided genuine advantages in direct combat. Its 75mm KUK-42 could penetrate any Allied armor at ranges exceeding 2,000 meters. Its sloped 80mm frontal armor was nearly impervious to most enemy weapons from the front. These were real capabilities that made Panthers fearsome opponents when they reached combat. But the operative phrase was when they reached combat. Panther reliability issues were legendary among German tankers. Final drive failures immobilized vehicles without warning. Transmission problems left formations stranded kilometers. From objectives, engine fires destroyed tanks without enemy action. And even when Panthers functioned correctly, their limited speed meant they couldn't redeploy rapidly to threatened sectors or pursue retreating enemies effectively. The M18, by contrast, simply worked. Its automotive systems, proven through millions of civilian vehicle production, rarely failed catastrophically. When problems occurred, repairs could be completed quickly with standard tools by moderately skilled mechanics. And its speed meant that even with lower operational readiness rates, M18 units could cover more ground and reach battle positions faster than Panther formations with higher readiness. Richter's final comparative analysis, completed on April 23 as Soviet forces entered Berlin's suburbs, stated the conclusion with Germanic directness. The American M18 tank destroyer represents superior industrial application of adequate technical principles. German armor represents superior technical sophistication hampered by inadequate industrial capacity and flawed reliability. In sustained operations, the American approach proves more effective. The report was filed and forgotten as Kummersdorf staff prepared to evacuate ahead of Soviet advances. The M18 itself was likely destroyed by German personnel before the Red Army overran the facility, though records are incomplete. The meticulous documentation survived, captured eventually by American forces, and archived with thousands of other German technical reports. The lessons learned at Kummersdorf, though documented thoroughly, arrived too late to influence German tank development. By spring of 1945, German industry had ceased meaningful tank production. Factories were being bombed systematically, raw materials had become unavailable, and transportation infrastructure had collapsed to the point where even completed vehicles couldn't reach combat units. But the technical assessments of the M18 revealed truths about armored warfare that extended far beyond Germany's immediate tactical situation. They documented a fundamental shift in how modern armies would think about mobility, protection, and firepower in the post-war era. The question wasn't whether thick armor or powerful guns mattered. The question was whether any vehicle could be armored sufficiently to guarantee protection, or whether mobility and tactical flexibility offered better survivability. American tank destroyer crews had answered that question empirically through thousands of combat engagements across Europe. The statistics, compiled meticulously by U.S. Army operational research teams, told a story that validated the entire tank-destroyer concept, even as traditionalists within the army questioned whether specialized anti-armor units remained necessary. Between June 1944 and May 1945, M18 equipped battalions engaged German armor in hundreds of documented encounters. The 704th Tank Destroyer Battalion, operating M18s throughout the European campaign, claimed destruction of over 300 German armored vehicles, including Tigers, Panthers, and assault guns. Their own losses totaled 31 Hellcats destroyed or damaged beyond field repair. The kill ratio exceeded 9-1 in favorable conditions. Even accounting for the optimism inherent in combat damage claims, the disparity was extraordinary. American crews, operating vehicles with armor that barely qualified as protection, were destroying German tanks designed to dominate European battlefields through technical superiority. The mathematical explanation was simple, but psychologically difficult for traditional armor officers to accept. An M18 that engaged from ambush, fired first, and withdrew immediately, had perhaps 90% chance of escaping undamaged. A German Panther that successfully tracked and returned fire at an M18 had perhaps 80% probability of scoring a mobility or firepower kill with the first hit, given the Hellcat's thin armor. But if the M18 escaped that first critical moment, the Panther couldn't pursue effectively, and the American crew could reposition and re-engage from a different direction. The cumulative effect over dozens of engagements strongly favored the vehicle that controlled engagement, timing, and location. German tankers, trained to fight set-piece battles where armor and firepower determined outcomes, found themselves forced into running engagements where those advantages became irrelevant. Their superior guns couldn't kill targets they couldn't catch. Their heavy armor provided no protection against enemies who never gave them clean shots. Technical Sergeant Robert Lotz, who commanded an M18 in the 630th Tank Destroyer Battalion through Belgium, France, and into Germany, described the tactical reality in a post-war interview conducted at Fort Knox in 1946. His account, preserved in Army archives, provided insight into how American crews thought about their vulnerability and advantages. "We knew the armor was thin. We knew any German gun could kill us if they hit square. That knowledge focused your mind wonderfully. You didn't take chances. You didn't trade shots with Panthers thinking your armor would save you. You used that speed for everything it was worth. See them first, shoot first, vanish before they even knew where you were. Do that right, and the thin armor didn't matter because they never got a shot." Lotz survived the war despite his M18 being hit twice by German fire. Once, an 88mm round passed completely through the rear hull without detonating, the high-velocity projectile encountering insufficient resistance to trigger its fuse. The crew bailed out immediately, expecting ammunition to cook off, but the vehicle remained intact. They returned to combat in the same Hellcat 2 days later, after maintenance teams patched the entry and exit holes. The second hit, a 75mm round, from a Panzer IV, struck the turret front at an oblique angle, deflecting upward and tearing away the gun shield without penetrating. Lotz credited luck and German desperation, firing at extreme range with his survival. But he also noted that in both cases, his crew had spotted the enemy first and was already moving when German gunners fired. The hits resulted from German skill and persistence, not from American tactical errors. This pattern repeated across hundreds of engagements, documented in after-action reports. M18 casualties generally occurred during chaotic close-range fighting, where speed advantages became neutralized, or during defensive stands, where tank destroyers were used contrary to doctrine as static anti-tank guns. When employed correctly as mobile hunters using speed and surprise, M18s proved devastatingly effective, despite vulnerability that would have been fatal in different tactical employment. The German perspective on facing M18s can be reconstructed from captured documents and post-war interviews with Wehrmacht veterans. General Lieutenant Heinz Eberbach, who commanded Panzer Group West during the Normandy campaign before capture in August 1944, provided frank assessment during Allied interrogation. "The American tank destroyers were unlike anything we had trained against. Soviet doctrine emphasized direct assault with heavy armor. British tactics favored coordinated maneuver with extensive infantry support. The Americans simply appeared from nowhere, fired, and vanished. Our Panthers could destroy them easily if we achieved engagement, but achieving engagement required predicting where they would appear next, and they moved too rapidly for our intelligence systems to track effectively. Eberbach noted that German units facing M18s began implementing modified defensive tactics, including more extensive patrol patterns and defensive depth to provide warning of American approach routes. But these adaptations consumed resources and limited German offensive capability, effectively achieving American strategic objectives even when Hellcats weren't actively engaging. The psychological impact on German crews shouldn't be underestimated. Fighting an enemy that could be anywhere, moving at speeds that made tactical prediction impossible, created persistent uncertainty that degraded combat effectiveness. German tankers, who'd learned to trust their superior armor and guns against Soviet and British opponents, found those advantages meaningless against Americans who refused to fight on German terms. Oberst Hans von Luck, commanding the 125th Panzer Grenadier Regiment during the Normandy fighting, described the frustration in his post-war memoir, published in 1989. We would establish defensive positions, dig in our tanks to maximize armor advantage, prepare overlapping fields of fire. Then American tank destroyers would appear from completely unexpected directions, fire into our flanks or rear armor, and disappear before we could respond. It was like fighting ghosts. Von Luck noted that his experienced crews, veterans of years of Eastern Front combat, felt more uncertain facing American tank destroyers than they had against numerically superior Soviet armor. Soviet attacks, however massive, followed predictable patterns. American hit-and-run tactics eliminated predictability, forcing German units to remain dispersed and defensive even when doctrinal principles called for concentration and offensive action. The industrial context made American tactical flexibility possible in ways that extended far beyond individual vehicle capability. The United States produced 2,507 M18 Hellcats between July 1943 and October 1944. This represented a tiny fraction of total American armored vehicle production during that period, which exceeded 50,000 tanks and tank destroyers of all types. Germany, fighting on multiple fronts with industrial infrastructure under systematic air attack, produced approximately 6,000 Panthers during the entire war and fewer than 1,350 Tigers of all variants. The numerical disparity meant that losing an M18 represented minimal impact to American combat power, while losing a Panther represented significant degradation of irreplaceable German armored strength. American crews understood this arithmetic, even if they didn't articulate it explicitly. An M18 destroyed in combat would be replaced within days or weeks. A trained crew, if they survived, would receive another vehicle and return to action. The Army could afford to trade vehicles for tactical advantage because industrial capacity ensured replacement. This knowledge influenced tactical decision-making, encouraging aggressive action that might seem reckless in an army that couldn't replace losses. German crews faced opposite incentives. Every Panther lost was essentially irreplaceable by late 1944. Experienced crews represented even more valuable assets than the vehicles themselves, given the collapse of German training infrastructure. This created psychological pressure to avoid risk, to preserve vehicles rather than employing them aggressively, exactly the opposite of what effective armored warfare required. The M18's mechanical reliability reinforced American numerical advantages. U.S. Army maintenance records from European operations indicate that M18-equipped battalions maintained operational readiness rates exceeding 70% throughout sustained combat operations. This meant that of every 10 Hellcats in a battalion, 7 remained combat-capable at any given time despite battle damage and mechanical wear. German Panther units, by comparison, struggled to maintain 50% operational readiness under similar conditions. Final drive failures alone accounted for roughly one-third of all Panther mechanical casualties, immobilizing vehicles that required complete drivetrain replacement before returning to service. Transmission problems caused another quarter of mechanical losses. These weren't battle damage. These were engineering and manufacturing deficiencies that German industry couldn't solve while simultaneously fighting a losing war. The practical impact meant that an American tank destroyer battalion with 54 M18s could expect to field 38 operationally ready vehicles on any given day. A German Panther battalion with the same nominal strength might field 27 combat-ready tanks, and those 27 would move slower, consume more fuel, and require more maintenance support than their American opponents. This mechanical reality influenced operational planning at every level. American commanders could execute ambitious flanking maneuvers and rapid advances, knowing their tank destroyer battalions would keep pace with armored spearheads. German commanders had to plan conservatively, assuming significant portions of their Panther strength would fall out due to mechanical failure during any extended movement. The reliability advantage became even more pronounced during winter operations. The M18's radial engine, designed originally for aircraft use, started reliably in extreme cold. Its automatic transmission functioned normally across wide temperature ranges. Its suspension components tolerated thermal cycling without failure. German tankers, conversely, dreaded cold weather that made their already temperamental vehicles even less dependable. During the Ardennes offensive in December 1944, German armoured units experienced catastrophic mechanical failure rates, despite initially achieving tactical surprise. Panthers broke down in enormous numbers as formations pushed westward through Belgian roads. The 116th Panzer Division reported 51% mechanical casualties among its Panthers within the first 3 days of operations, before significant American counterattacks began. American tank destroyer battalions, rushing northward to reinforce threatened sectors, maintained operational tempo throughout the crisis. The 705th Tank Destroyer Battalion moved over 200 kilometers in 36 hours to reach defensive positions near Bastogne, arriving with 41 of 48 M18s operational. This strategic mobility, enabled by vehicle reliability and speed, proved as valuable as firepower in containing German penetrations. Hauptmann Weber, reflecting on his testing experience at Kummersdorf during a 1947 interview conducted by American historical officers, acknowledged that German tank design had pursued wrong priorities. "We built magnificent machines when they worked, but we needed vehicles that worked reliably under all conditions. The Americans understood this. We did not, or we understood too late to matter." Weber noted that his experience driving the captured M18 had convinced him that automotive excellence mattered more than maximum performance specifications. "I had commanded Panthers that could destroy any Allied tank at 2,000 meters. But what good was that capability when the Panther broke down before reaching the battlefield? The Americans built adequate vehicles that reached battle and functioned when needed. That proved more valuable than our superior vehicles that too often failed when needed most." This assessment, from a German officer with no reason to flatter American equipment in private interviews conducted after Germany's defeat, carried weight that propaganda claims never could. Weber had commanded German armour in combat, understood its capabilities and limitations through direct experience, and tested American equipment under controlled conditions, allowing objective comparison. His conclusions matched mathematical analysis of combat results and operational statistics. The M18 Hellcat's legacy in American armor doctrine proved complex and ultimately contradictory. The vehicle itself performed brilliantly throughout European operations, validating tank destroyer doctrine and demonstrating that speed could substitute for armor when paired with appropriate tactics. But the Army's post-war assessment concluded that specialized tank destroyer battalions represented inefficient organization, and the entire tank destroyer branch was eliminated in 1946. This decision reflected changed strategic circumstances rather than failure of the M18 concept. The threat that had motivated tank destroyer doctrine in 1941, German panzer divisions breaking through American lines and requiring rapid mobile response, had proven less severe than anticipated. American tank battalions equipped with Shermans proved capable of handling most anti-armor missions, making specialized tank destroyer units redundant organizationally. but the tactical lessons survived institutional reorganization. The principles of mobility as defense, engagement control through speed, and hitting from unexpected directions migrated into mainstream armor doctrine. Post-war tank development increasingly emphasized mobility alongside protection and firepower, recognizing that stationary targets died regardless of armor thickness. The M18 influenced American armored cavalry doctrine developed during the 1950s and 60s. Cavalry units, responsible for reconnaissance and screening missions, employed light armored vehicles using tactics that would have been instantly recognizable to Hellcat crews. Move fast, observe without being observed, engage opportunistically when favorable, withdraw before enemy forces could mass against you. The M18 had proven these principles worked against first-rate opponents in the world's most intense armored combat. Soviet observers, studying American tank destroyer employment through captured German documents and debriefings of Wehrmacht prisoners, drew their own conclusions. The PT-76 amphibious light tank, entering Soviet service in 1952, reflected obvious influence from American speed over armor philosophy. Its thin armor and relatively light gun emphasized mobility and rapid deployment over heavy protection. Soviet doctrine never formally acknowledged borrowing American concepts, but the parallel development was unmistakable. Soviet airborne and naval infantry forces received vehicles designed for rapid movement and opportunistic engagement, exactly the mission profile the M18 had executed successfully. The tactical employment guidance could have been translated directly from American tank destroyer manuals, emphasizing speed, surprise, and withdrawal before enemy forces could respond effectively. The M18 itself served with American forces through the end of World War II and immediately into occupation duties in Germany and Austria. Approximately 1,800 Hellcats remained in Army inventory when Japan surrendered in August 1945. None saw combat in the Pacific theater, as tank destroyer doctrine had developed specifically for European fighting conditions, and Japanese armored forces posed insufficient threat to justify specialized anti-tank units. Post-war, most M18s were scrapped or transferred to Allied nations under military assistance programs. Yugoslavia received approximately 100 Hellcats in 1951, using them for border security and internal security missions until retirement in the late 1950s. The vehicles fit Yugoslav doctrine emphasizing light mobile forces capable of rapid response across mountainous terrain where heavier armor couldn't operate effectively. Venezuela acquired 56 M18s in 1952, valuing them primarily for their impressive specifications and intimidating appearance rather than genuine combat capability. Venezuelan Hellcats served mainly ceremonial roles, appearing in parades and military demonstrations. The vehicles were retired in 1964 when spare parts became unavailable and replacement with more modern equipment became economically feasible. Pakistan obtained a small number of M18s in the 1950s, though records are incomplete regarding exact quantities and service history. The vehicles likely served in training roles, familiarizing Pakistani crews with American equipment before more modern armored vehicles became available through military assistance programs. None saw combat during Indo-Pakistani conflicts, having been retired before hostilities began. The last M18s in active military service were likely those operated by Yugoslavia, which retired its final Hellcats around 1958. By then, the vehicle's wartime capabilities had become obsolete. Post-war tank development had produced armor too thick for the 76mm gun to penetrate reliably. Anti-tank guided missiles offered superior standoff range and penetration. The M18's speed advantage, dramatic against 1940s opponents, seemed less impressive compared to new light armor designs. But obsolescence as frontline combat equipment didn't diminish the M18's historical significance. The vehicle had proven concepts that reshaped armored warfare thinking. It demonstrated that mobility could substitute for protection when paired with appropriate doctrine. It showed that automotive engineering excellence enabled tactical flexibility, and it revealed that adequate technology, mass-produced and deployed in overwhelming quantities, defeated superior technology produced in insufficient numbers. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The captured M18 at Kummersdorf, that single vehicle driven repeatedly by Hauptmann Weber and examined exhaustively by Oberingenieur Richter, represented more than enemy equipment brought home for analysis. It was physical proof that American industrial capitalism, with its emphasis on practical manufacturing efficiency and mass production, could produce military equipment superior in aggregate to anything German engineering perfection could achieve within their industrial constraints. Weber had understood this by April 1945, watching the M18 accelerate away at speeds his Panthers couldn't match. Richter had documented it in hundreds of pages of technical reports, noting American automotive excellence applied to military requirements. German industry had known it intellectually since at least mid-1943, when Sherman testing revealed similar patterns. But knowing a problem and solving it represented different orders of difficulty. Germany lacked time, resources, and industrial infrastructure to retool production toward reliability and maintainability by 1944. The nation that had started the war with technical advantages in many weapons systems had lost the industrial war through inability to translate those advantages into sustained mass production of reliable equipment. The United States, entering conflict with less sophisticated weapons in many categories, won through superior manufacturing capability, producing adequate equipment in overwhelming quantities. The M18 Hellcat exemplified this American approach perfectly. Not the best armored vehicle theoretically possible, not equipped with the most powerful gun available, not incorporating the most advanced technology German engineering could design, but reliable enough, fast enough, and produced in sufficient numbers to accomplish its mission decisively against Germany's best equipment. 55 miles per hour, maximum speed, 76mm gun adequate for killing any German armor from favorable angles. Armor sufficient to stop shell fragments and small arms fire, but nothing heavier. Automatic transmission allowing any competent driver to operate effectively. Radial engine that started reliably and ran consistently. All integrated into a package that cost less to build, required fewer resources to maintain, and could be produced faster than German alternatives. These weren't the specifications that German engineers would have chosen if designing a tank destroyer from scratch. They were the specifications that American industry could deliver reliably at scale, and they proved sufficient for decisive battlefield superiority when employed according to doctrine emphasizing mobility and tactical flexibility. The mathematics remained brutal and clear when examined objectively decades later. An adequately armed, lightly armored vehicle that reliably reached the battlefield and fought effectively beat a theoretically superior vehicle that broke down before engaging or couldn't be produced in sufficient numbers. Mobility combined with appropriate tactics beat heavy armor when the mobile force controlled engagement terms. Industrial maturity, expressed as mechanical reliability and manufacturing efficiency, beat engineering sophistication, applied within inadequate industrial capacity. Germany had learned these lessons through painful experience, documented them thoroughly through testing at facilities like Kummersdorf, and lacked means to apply that knowledge before defeat. America had understood them intuitively through decades of automotive industry development, applied them systematically to military vehicle design, and leveraged that advantage to help win history's largest industrial war. The captured M18, driving faster than German staff cars around that testing track in Brandenburg, while Soviet artillery rumbled closer each day, told the entire story. By April 1945, it hardly mattered anymore. The war was ending regardless of technical assessments or tactical innovations. But the lessons documented at Kummersdorf survived Germany's defeat, influencing post-war armor development and validating doctrines that redefined how modern armies thought about mobility, protection, and firepower. Hauptmann Weber, who'd commanded Panthers through years of bitter fighting, had recognized truth in that impossibly fast American vehicle with its thin armor and straightforward engineering. He'd watched it accelerate away at speeds that made mockery of German tank doctrine, and he'd understood with painful clarity that Germany had lost the industrial war before the shooting started. The M18 hadn't won through technical superiority. It had won through industrial excellence expressed as reliable mechanical performance, and that proved more valuable than any number of impressive specifications on paper. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.